In the last lecture, we were discussing momentum conservation, okay, and I had derived for you the momentum conservation equation. Okay. Okay. So, here the two important quantities are the stress sigma, okay, which I said is a second order tensor. Okay. It has 9 components, 2 indices. The first index corresponds to the direction of momentum and the second index corresponds to the direction of transport. It can be written in matrix form as sigma xx, sigma xy, and from the angular momentum conservation, this is constrained to be symmetric. That is, the off diagonal components are all necessarily equal. Okay. In the absence of flow, the stress is what is called an isotropic tensor. It contains only the pressure as its diagonal elements. Pressure minus P, because pressure is defined to be positive when it is compressive, whereas the stress is considered to be along the outward unit normal. Therefore, the stress is positive when it is extensional. Okay. So, therefore, you have a minus pressure. Okay. In short form, this can be written as minus P times the identity tensor, where the identity tensor is 1 along and 0 off diagonal. Okay. In the presence of flow, the stress consists of minus P minus P I plus what is called the shear stress, okay, plus what is called the shear stress. And this shear stress is related to the rate of deformation through the constitutive relation, that is Newton's law. Okay. The Newton's law states that the stress is proportional to the gradient in the velocity. Okay. So, the rate of deformation tensor gradient of the velocity. Okay. So, this also has 9 components. Note that there is no dot product here between the velocity and the gradient, and this basically tells us that if we are at a location x and the velocity is in some direction, and if we go to a small distance x plus delta x and we have the velocity in some other direction v, okay, then the difference in velocity, that is v vector at x plus delta x minus v vector at x is equal to delta x dotted with grad v. Okay. Definition of the gradient: velocity is a vector, it is not a scalar like it was in the concentration and temperature equations. Okay. This velocity gradient vector, the velocity gradient second order tensor, okay, partial Vx by partial x okay, 3 by 3. Okay. This we said this is a second order tensor. Of course, I have omitted the unit vectors before, the row of unit vectors before and the column of unit vectors after. Okay. It is understood that they are present. Okay. This can be written as the sum of an antisymmetric tensor, okay, plus a symmetric traceless tensor plus an isotropic tensor, which is basically 1/3 divergence of velocity times I. Okay. Where this antisymmetric tensor, okay, antisymmetric matrix is equal to 1/2 of gradient of velocity minus gradient of velocity transpose, where the transpose represents the interchange of the row and column indices. Okay. The transpose represents the interchange of the row and column indices. Okay. This symmetric traceless part, okay, is equal to 1/2 of grad V minus grad V transpose minus 1/3 del dot V into the identity tensor. Okay. And you can easily verify that this one plus this expression plus this expression, in the end if you add all of them up, you will in fact get the gradient of the velocity vector. Okay. So, you can verify that. Okay. So, each of these represents different forms of deformation. Okay. Okay. The first is the isotropic tensor. Okay. This represents radial expansion or compression with respect to the origin. Okay. I had shown you that. Okay. This represents radial expansion or compression. Okay. And this divergence of velocity from the mass conservation equation can be written as partial rho by partial t plus the divergence of rho times v, that is v dot grad rho plus rho del dot v equal to 0. Okay. And from this I can get quite simply that del dot v is equal to minus 1 by rho d rho by dt. Okay. Divergence is positive, the density decreases, d rho by dt is negative. Okay, because there is volumetric flow outwards, okay, the volume expands, mass is a constant, therefore, the density has to decrease, and vice versa. When del dot v is negative, the density increases. Okay. The second part was the antisymmetric tensor, okay, this which is 1 by 2 of grad v minus grad v transpose. Okay. And I had shown you that this corresponds to solid body rotation, okay, of nearby points. Okay. If you go a small distance delta x along the x axis, this basically corresponds to solid body rotation. Okay. Okay. And I had also shown you that this can be written in terms of the vorticity vector. Okay. This is equal to 1/2 omega cross delta x vector, where delta x vector is the displacement from the origin. Okay. Okay. If you had a solid body rotating with angular velocity omega, then the linear velocity, okay, so I am sorry, I should, yeah, okay. So, I should write this as not antisymmetric, this is delta v, okay. The difference in velocity between 2 points separated by delta x, okay, due to the antisymmetric part of the rate of deformation tensor can be expressed as 1/2 of the vorticity cross delta x, where the vorticity is equal to the curl of the velocity vector. Okay. This form of the equation is the same as you would have if you had a solid body rotating, okay, with angular velocity omega. Okay. Angular velocity omega whose axis is perpendicular to the plane. Okay. In that case, the velocity, the linear velocity at any point v, okay, so it will be along the direction of rotation tangential, this v will be written as omega cross delta x, okay, where delta x is the displacement. Okay. Comparing these two, you can see that the form of the deformation due to the antisymmetric part of the rate of deformation tensor is the same as solid body rotation with angular velocity equal to 1/2 of the vorticity, okay, with angular velocity equal to 1/2 of the vorticity. And finally, there was the third component that we had to that we had separated into, which is the symmetric traceless part of the rate of deformation tensor. Okay. And I showed you that this basically corresponds to, okay, if I had a volume that was originally like this, okay, this is x and this is y. After some time, this will contract in one direction, expand in the other direction in such a way that the total volume is conserved, okay, and there is no rotation of the axis. Okay. So, this is what is called extensional strain. So, I divided the rate of deformation tensor into three components. One is the expansional, one is the solid body rotation, and the other is the extensional strain. Newton's law of viscosity is derived assuming that there is a linear relationship between the stress and the, okay. Of course, you cannot just write a simple relation like sigma is equal to some constant times grad v, okay, because the left side is constrained to be symmetric, whereas the right side is not. Okay. So, the stress can only depend upon, okay, the stress can only depend upon the symmetric traceless and the isotropic parts of the rate of deformation tensor. Okay. So, I should note that this is the shear stress, this is not the so if I write the total stress, I will have the isotropic part first, the pressure which is present even in the absence of flow, plus a part that is proportional to the symmetric traceless part of the rate of deformation tensor, plus a part that could be proportional to the isotropic part. Okay. This one will just give you divergence of velocity times the identity tensor. So, this is this is an isotropic tensor, where mu is what is called the coefficient of viscosity, okay, sometimes called as the coefficient of shear viscosity, and mu b is often called as the coefficient of bulk viscosity. Okay. For the particular case where the flow is incompressible, okay, for the particular case where there is an incompressible flow, the divergence of the velocity has to be equal to 0. Okay. The divergence of the velocity has to be equal to 0, which means that this term here is equal to 0, okay, and in the symmetric traceless part, half of grad v plus grad v transpose minus 1/3 I divergence of velocity, this term is also equal to 0. Okay. And then basically the stress is equal to minus p I plus mu into grad v plus grad v transpose. Okay. So, that is what you will get for the symmetric traceless part. Okay. And then we had gone on to substituting this into the Navier-Stokes momentum conservation equation. Okay. Just to recall, mass conservation equation partial c by partial t plus del dot v c is equal to minus divergence of j plus any source. Okay. That was the mass conservation equation. Now we have to write it for the momentum conservation. Turns out it has a similar form, okay, partial rho by partial t plus divergence. So, I should be careful here, okay. Sorry. Partial of rho v by partial t plus the divergence dotted with rho v and v, okay, indicating that this divergence symbol is acting on one of the velocities, okay. This divergence symbol is acting on one of the velocities, okay. This is equal to minus divergence of sigma plus plus the body force density F plus the body force density F. This left hand side, if you recall, we had simplified, okay. So, the first term partial rho by partial t okay, that is the first term on the left. Second term divergence okay. I had written this for you as v vector divergence of by differentiation by chain rule okay, plus okay, okay, differentiation by chain rule. In this first term here, divergence is dotted with the velocity itself. Okay, in this first term here, the divergence is dotted with the velocity itself. In this second term, the velocity before the divergence is dotted with the divergence, and the vector direction is with this velocity vector. Okay. Okay. So, differentiation using chain rule. Okay. And if I add up these two, okay, if I add up these two, okay, okay, this gives me v vector into partial rho by partial t plus okay, plus the second terms plus rho into partial v by partial t plus v dot grad v, okay, and this entire first term is 0 because of mass conservation. Okay. So, mass conservation equation is partial rho by partial t plus divergence of rho times v is equal to 0. Okay. So, therefore, the left side basically becomes rho times partial v by partial t plus v dot grad v is equal to del dot sigma plus f vector. Divergence of sigma, okay, is divergence of minus p times the isotropic tensor plus mu into grad v plus grad v transpose. Okay. Now, this first term is the divergence that is will just write it here for you for simplicity. Ex partial by partial x plus Ey partial by partial y plus Ez partial by partial z dotted with the identity tensor. Okay. Identity tensor has diagonal elements non-zero and off diagonal elements are 0. So, this can be written in dyadic form as Ex plus Ey plus Ez. Okay. And if you use the property that Ex, Ey and Ez are perpendicular to each other, okay, you can easily do the dot product. Okay. A first order vector with a second order tensor, Ex dot Ex is 1, Ex dot Ey is 0 and so on, and you will basically get Ex d by dx plus Ey d by dy plus Ez d by dz. Okay. So, that is the gradient. Okay. So, this is equal to minus gradient of pressure plus, okay, viscosity is independent of position. If it is dependent on position, this should be written as mu into grad V plus. If it is independent of position, I can take it out minus grad P plus mu. Note that in this term the dot product is between the gradient. Okay. The dot between the gradient and the gradient. So, I get del square V. Okay. I have to take the transpose of the velocity. I have to interchange the row and column. That means that the dot product is between the gradient here and the velocity here. Okay. That means that the dot product is between the gradient and the velocity, because I have to take the transpose. So, I will get mu grad of del dot V. Okay. And this thing is 0 for an incompressible fluid. Okay. Divergence of velocity is 0 for an incompressible fluid. Okay. So, putting all this together, I will get rho into partial V by partial T plus V dot grad V is equal to minus grad P plus mu del square V plus F. Okay. So, that is the mass conservation equation together as I am sorry, this is the momentum conservation equation, which together with the mass conservation equation, divergence of velocity is equal to 0 for an incompressible fluid, is what is called the Navier-Stokes mass and momentum equations. Okay, the Navier-Stokes mass and momentum conservation equation. So, okay. You can get form of these equations called inviscid irrotational flow. Okay. Inviscid, no viscosity. So, this basically says that the viscosity is equal to 0. Okay. Irrotational, that means there is no rotation. That means that this basically says that the gradient of the velocity vector is symmetric. As I said, rotation was associated with the antisymmetric part of the rate of deformation tensor. So, irrotational means that this is symmetric. Okay. In that particular case, since there is no rotation, it turns out that you can express the velocity, okay, is equal to the gradient of a potential. Okay. So, del dot V is symmetric and the vorticity is equal to 0. Okay. Vorticity, which is the curl of the velocity. Okay. The vorticity, which is the curl of the velocity, has to be equal to 0, because I told you that for the rotational part, the antisymmetric part of the rate of deformation tensor can be expressed as half omega cross delta x. So, if the antisymmetric part is 0, that means all three components of the vorticity are 0. Okay. If that is the case, you can express the velocity as the gradient of a potential. Okay. This you can verify automatically satisfies the vorticity is equal to 0, okay, and substitute that into the momentum conservation equation. Okay. So, if I substitute this into the momentum conservation equation, which is given here, okay, then I get rho into partial by partial t of grad phi, okay, writing the velocity as the gradient of a potential as shown here. Okay. Okay. Plus rho, okay, v dot grad v is equal to minus grad p. Okay. There is no viscous term, viscosity was equal to 0. So, this term does not exist, okay, plus F vector. Okay. So, this is what the equation reduces to. So, let us see how to simplify this second term here, rho v dot grad v. Okay. I can also write this, since the rate of deformation tensor is symmetric, there is no rotation, that implies that gradient of velocity is equal to gradient of velocity whole transpose. Okay. That gradient of velocity is equal to its transpose. Okay. Therefore, I can as well write this as rho v dot grad v transpose. Okay. Now, the dot product is between this velocity vector and this velocity vector, okay, because there is now a transpose. Okay. So, if I expand this out, okay, so what I will get is equal to, for example, when I take the x component, I will get Vx Ex partial by partial x of Vx, okay. That is for the velocity x component and the gradient x component, plus, okay. Note that the dot product here is between these two, that means that these two indices have to be the same, okay. And there is a summation, because in the dot product there is a summation over x, y and z, okay, plus Vy Ex partial by partial x of Vy plus Vz Ex partial by partial x of Vz. Okay. Plus you will have two more rows where you replace this Ex d by dx with Ey d by dy, okay, and Ex d by dx with Ez d by dz. Okay. So, okay, so you will get a total of 9 terms in this, okay, where the indices of this velocity and this velocity are dotted, okay, and the free unit vector comes from this gradient vector. Okay. This first term can be written as Ex partial by partial x of half Vx square plus Ex of half Vy square plus etc., okay, plus, okay, the other two terms. Okay. Okay. Half Vx square plus half Vy square plus half Vz square is half V square, where V is the magnitude of the velocity. So, I will get Ex of half V square d by dy of half okay. And this, as you can see quite easily, is just equal to gradient of half V square. I am sorry, I missed out a factor of rho everywhere. So, the density has to be there in all of these terms. Okay. Okay. So, therefore, my momentum conservation becomes equation becomes rho into partial of grad phi by partial t plus grad of half V square is equal to minus grad P plus F. Okay. In this first term here, I can interchange the order of differentiation because time and position are two independent variables. Therefore, I can interchange the order of differentiation and write this as gradient of partial phi by partial t. Okay. And if the force is conservative, then it can be written as minus the gradient of a potential. Okay. Minus the gradient of a potential energy. Okay. And since density is a constant, I can write this entire equation taking the gradient outside as rho partial phi by partial t plus rho by 2 v square plus p plus phi. This is equal to 0. Okay. If the gradient of a quantity is equal to 0 at each position in space, that means there is no variation with respect to neighboring points at each position in space, that means that that quantity is a constant. Okay. Is equal to some constant P naught. Okay. This is what is called the Bernoulli equation. Okay. This is what is called the Bernoulli equation. For the pressure. Okay. That is the momentum conservation equation for inviscid irrotational flow. This has to be combined with the mass conservation equation is equal to 0, which implies that del dot grad phi is equal to 0, which implies that del square phi is equal to 0. That is, the Laplacian of the potential is equal to 0 and the pressure is related to the potential through the Bernoulli equation. Okay. And these two together are what are called the potential flow equations. For inviscid, there is no viscosity, and irrotational. There is no rotation in the flow field. So, for an inviscid irrotational flow, simplification of the momentum conservation equations is the Laplace equation for the velocity potential, where the velocity is equal to the gradient of the potential, and the Bernoulli equation for the pressure. So, with this we complete our discussion of the Navier-Stokes equations and its simplification, the potential flow equations. In the next lecture we will start looking at some simple flows, okay, time dependent, unsteady, and spatially varying only in one direction. These are what are called unidirectional flows. Okay, they vary only in one direction and in time. We will start this in the next lecture, the application of the equations that we have derived to steady unidirectional flow, unsteady unidirectional flows. I will continue this in the next lecture. I will see you then.